Okay, so once again, consider a rectangular coil of wire of length A, that's the length A, and width B, carrying a current I in the direction indicated. On the left side the current is upward, on the right side the current is downward. Alright, what happens? The force on the left side of length A will be, what will be the amount of force? Will be IAB directed into the paper. Now, how do you find that direction? Look at that again. The current is upward. The direction, can you follow what I'm doing here? That is the direction of the current upward. The field is that way. So, if you look at that, the current upward, the field is that way. Therefore, the force will be into the board. So, the force on this side will be into the board, and the force on the other side will be out of the board. So, the force on the right side will be F2 equal to IAB directed out of the paper. Now, each of these forces produce a torque on the coil about an axis through its center. This is the axis of the coil, and as a result, the coil will rotate about that axis. The torque of F1 will be, remember, if the force here is directed into the board, the torque will be that force multiplied by this distance, which is half of B. So that will be IAB times 1/2 B. And that can be simplified as 1/2 I uppercase A. Now, the lowercase a times lowercase b is length times width, which is the area of this coil. So A times B is replaced by the uppercase A, the area of the coil. So the torque of F1 is 1/2 IAB. I is the current, A is the area of the coil, and B is the magnetic field. Now the torque of the other force, F2, similarly will be 1/2 IAB. So here I have the torque due to one force and the torque due to the other force, both about this axis, and therefore what is the net torque? The net torque will be the sum of these two, which will be I times A times B. So when a coil of total area A is placed in a magnetic field B and a current I passes through that coil will experience a torque given by tau equal to IAB, and it will rotate. Now, that is if the coil has just one turn. If the coil has n turns, the total torque will be NIAB. That's an important relation. Now the quantity NIA is a vector, and that vector is normal to the plane of the coil and is called the magnetic moment and be represented by mu. So the quantity NIA is called the magnetic moment of the coil, and therefore tau can be written as tau equal to mu B, where mu is called the magnetic moment of the coil. Now, if theta is the angle between the direction of B and the normal to the plane of the coil, then I can write tau equal to, that means if theta is the angle between B and the normal to the plane, that's the angle theta. then tau will be NAIB sine theta. Now remember, when this theta is 90 degrees, the sine theta is 1, and the tau will be NAIB, which is mu times B. If theta is other than 90 degrees, then tau will be NAI. You can see that I have a small printing error there. That A must be uppercase A, area of the coil. N uppercase A IB sine theta. And that can be written as mu cross B, because NAI is the vector called the magnetic moment of the coil. That is. So the torque experienced by a coil carrying a current placed in a magnetic field is mu cross B. And I've illustrated that concept here, why the torque actually occurs. The catapult effect, which we talked about a while ago. Let's do a small problem. A rectangular coil of wire of length 5 centimeter and width 3 centimeter is made up of 22 turns of a conducting wire. The current in the coil is 3.2 ampere, and the axis of the coil makes an angle of 37 degrees with the magnetic field of 500 Tesla. Calculate the magnitude of the torque on the coil. That's a very simple problem, is that right? Well, first we obtain the area of the coil. We know the length of the coil, we know the width of the coil. Therefore, the area of the coil, which is the uppercase A, is length multiplied by width, and that is 1.5 times 10 to the negative 3 meters squared. And the magnetic moment is therefore NIA. Is that right? That's the quantity we call mu, which is the number of turns multiplied by the current times the area. And that is 22 times 3.2 ampere times that area. That is 0.106 ampere meter squared. Well, we need to find the torque. And the torque is mu B sine theta. Is that right? NIAB sine theta. NAI is the magnetic moment. So tau equal to mu B sine 37 degrees. And we know all those quantities. That gives you 31.8 meter Newton. Another problem. A current carrying wire is bent in the form of a square of side 6 centimeter and is placed in the XY plane. It carries a current I equal to 2.5 ampere. What is the torque on the wire if there is a uniform magnetic field of 0.3 Tesla in the Z direction and 2 in the X direction? Well, remember, the force will depend on the direction of the field. Well, we have a N equal to 1. It's a one-turn coil, and the side of the square is 0.06 meter, means its area will be the square of that, 0.0036 meter square. The current is given. The magnetic field is given, and since the coil is in the XY plane, the normal vector, well, the XY plane is, well, that's the XY plane. The normal vector will be K, is that right? So, N, the normal vector is K. The magnetic moment is NAIK. It's a vector in the K direction. And that will be, and we know the area of the coil we calculated, and the current is given. Therefore, the magnetic moment is 0.009 K. Now in the first case, the field is in the z direction. That means the angle theta is 0. The angle theta is the angle between the direction of the field and the direction of the normal vector to the plane. So this is the xy plane. The normal is a z vector. That means in the first case, the angle between B and N is 0. If the angle is 0, sine 0 is 0. Therefore, torque will be 0. On the other hand, when B is in the x direction, that angle will be 90 degrees. And therefore, the torque will be mu B sine 90 degrees. That will be 0.0027 J meter Newton. So what that means is, when the coil is in the direction it is 0, there is no torque. But when the coil makes an angle of 90 degrees, the torque will be a maximum. I illustrated that to you earlier. Now here we have now the concept of an electric motor. Well, if a coil of wire is placed in a magnetic field, that coil will experience a torque and rotate, and that is how an electric motor is made. So the torque experienced by a coil of wire carrying a current placed in a magnetic field can produce continuous rotation. Now, this principle of working, this is actually the principle of working of an electric motor. I have actually explained that principle here. Now, if I can wind a coil of wire on a frame like this and place it inside a magnetic field, there's a magnet, there's a north pole and a south pole there, so that the coil is inside a magnetic field. And then when a current is allowed to flow, the coil will rotate. But there is a problem. And what's the problem? If the current flows on the right towards me, then the current on the left will go away from me. So if the force on this is downward, the force on the other side will be upward, right? After half a rotation, well, the force on this side will be downward. So how would you get a continuous rotation? The only way to get continuous rotation is when it completes half a rotation, the direction of current must change. The current that was flowing towards me on this side, when it completes half a rotation, the current must be in the opposite direction, so that the force will change. Now, I have actually made a contraption, and I would like to show it to you before I close the lesson today. Now here I have made this coil, and the ends of the coil are connected to these brushes. And when I connect those brushes to the battery, what happens is the brushes, the right brush which is in contact with the positive, when it rotates after half a rotation, it will come and make contact with the left brush. That means for every rotation, the direction of the current will change, and I will get continuous rotation. Now watch this when I make that connection. There you are. I get continuous rotation by changing the current halfway through. And the current is changed by using these brushes. So the electric motor, the brushes are very important. Alright. Alright, I hope you enjoyed this lesson. We will continue this concept again in the next lesson.